For our calculus project, we're interested in finding real-life applications of calculus problems we've done in class. One example of this is a problem where someone had to find the optimal time to reach a certain point on Greenway.
After finding a study conducted by Indiana University that said that dogs inherently find the quickest path to a ball, we decided to figure this out ourselves.
We hypothesized that dogs would inherently find the quickest time it took to get to the ball, but to test this hypothesis, we had to do the calculus ourselves.
The main focus of our calculus project is the application of optimization in the real world. Optimization is using the first derivative to find absolute minimums and maximums of an equation. Optimization problems we've done in the past are finding the largest area of a rectangle under a curve, the shortest path to a certain point, or the greatest volume of a tank of water. These optimal points are bound by certain constraints. Our project, similar to a problem we previously did in class about Green Lake, optimizes the time it takes the dog to get to a ball thrown into water. Given the dog's running and swimming rates, we formed an equation for the total amount of time it would take the dog to reach the ball. To optimize this equation and find the shortest amount of time possible, we derived the first equation and set it to 0. We made sure to take the second derivative of the equation, which was positive, to make sure the value we were calculating was in fact the minimum amount of time.
In order to optimize the time taken running and swimming respectively, we'll first start with the diagram. Here, if we look at the diagram, point A is the position both where the dog starts and where the ball is thrown. Point B is the position where the ball lands, and point D is the position where the dog enters the water. With these pieces of information, we can then label the distances in terms of variables x, y, and z for ease when calculating. Thus, with our diagram, we can then begin to write our initial equation. We know that distance equals rate times time, which can be written as time equals distance over rate. Here, we can then say the total time taken will be the distance running, z minus y, as shown from the distances in the previous diagram, divided by the rate of running r, plus the distance swimming, which is the square root of x squared plus y squared, which we got from the Pythagorean theorem, divided by the rate of swimming s. Then, in order to optimize, we will take the first derivative and set the equation equal to 0. Next, we will rearrange the equation in order to solve for y. Remember the previous diagram. Solving for y will allow us to figure out the optimal time and distance running and swimming, which we can then compare to our own dog to determine our result. We'll start by squaring both sides to get rid of the square root. Next, we'll cross multiply to get rid of the fractions. Then, we'll separate like terms. Then, we can refactor. Then, we'll isolate the y variable. Next, we'll divide by s squared. We do this in order to bring the s squared to the bottom of the fraction, cleaning up the equation. Finally, we'll square both sides and be left with an equation in terms of y. Then, once we determine real data from the experiment, we'll be able to plug our own rates in and determine the actual optimization. In order to actually conduct this experiment, we first timed our dog Max, running a set distance 5 times, and averaged these times to get his running rate. We did the same thing to find his swimming rate, by tying string to a tennis ball, throwing it, and measuring the time it took him to travel the distance of the string. We also conducted this 5 times to ensure accurate results. Once we had each of these rates, we set up an image like that of the diagram shown previously with a tape measure running down the length of the beach parallel to the water. Madison would start at what would have been point A, or the base of the tape measure, and throw a tennis ball connected to a string at an angle out into the water. As soon as the ball hit the water, she would grab the string in order to measure the length of the hypotenuse of the triangle. While this was happening, I would stand right next to Madison while holding our dog, Max. When Madison threw the ball out into the water, I would release Max and run after him, marking the point, which would have been point D on the diagram, where he entered the water to chase after the ball. Meanwhile, Sharanya would measure the distance perpendicular to the shore where the ball entered the water. This would have been point C on the diagram. We repeated this process 10 times to ensure accuracy, though there were several variables we were unable to control. We'll discuss these later. With these 3 distances and the rates of swimming and running, we were then able to determine if Max does indeed know calculus.
We realized that there are assumptions that we made when we found our data and calculated our results. First, we assumed that Max's running and swimming speeds stayed constant the entire time. Although we calculated the averages of these speeds, we still don't think that he maintained the same speed throughout the whole experiment.
We also assumed ideal conditions, which clearly were not what we had. So the presence of waves could have had 2 major effects on our data. The first being that the ball was probably moved inshore a little bit after it was thrown, and during the duration of time when Max was running to get to the ball, the string was also probably altered because of the waves, which wouldn't give us a clear straight line of the hypotenuse of the triangle, which we were measuring.
Finally, we made the assumption that Max was actually swimming in the water, but because he's such a large dog, the first couple steps of his strides into the water often were him running in the waves instead of actually swimming.
Taking these assumptions into account, we can now analyze our results. We found that although Max is a very smart dog, he did not effectively do calculus. The graph that you're looking at shows an orange linear approximation of the optimal location of y given the distance from the ball to the shore. The blue data points indicate the location that Max actually entered the water at each given distance. On average, Max entered the water 3 to 4 meters earlier than our calculated optimal point, but as you can see from the data, there was a lot of variation on exactly how early he entered, ranging from 0.2 meters to about 10 meters. The second derivative was also in fact positive, which is important for our equation because it proves that when setting the equation equal to 0, we found a minimum and not a maximum for the time to the ball.
In conclusion, we found that Max got overexcited and entered the water early, indicating that he was not actually doing the calculus.
However, we would like to acknowledge that this is not indicative of all other breeds of dogs or other dogs, so it is definitely possible that a different dog would be better able to optimize the time to the ball.
Thus, we encourage you to try this experiment with your own dog and see what results you get.